Welcome to the Deep Dive, the show where we plunge into complex topics, meticulously break them down, and extract the most vital nuggets of knowledge, all to ensure you walk away feeling truly well-informed. Today, we're navigating an invisible frontier that's fundamental to our modern lives, the bustling, unseen highways of wireless communication. Think about it, from the smartphone in your pocket to the smart home devices around you, even the medical sensors that monitor our health, they all rely on these unseen airwaves.
But here's the crucial, perhaps unsettling question we're going to tackle. What happens if these vital invisible highways become dangerously congested, or worse, are
This insatiable demand for wireless communication and ever higher data rates puts immense pressure on a surprisingly finite resource, the radio spectrum itself.
And that's the core tension, isn't it? Radio spectrum isn't some limitless, ethereal expanse. It's a very real, finite, natural resource, much like arable land or clean water. And because it's so critical, it's typically governed and managed by powerful regulatory bodies like the Federal Communications Commission or
FCC here in the U.S. These organizations meticulously allocate specific frequency bands for specific uses, a bit like designating specific lanes on a physical highway for truck.
Provocatively call spectrum holes.
Spectrum holes, okay.
Imagine a multi-lane superhighway where 80% of the traffic is crammed into just 2 lanes, leaving 8 other lanes wide open but formerly off limits. That's a massive amount of wasted capacity.
And that wasted potential is precisely where the true ingenuity of cognitive radio, or CR, shines through as a transformative solution. This isn't just about tweaking existing systems, it's about fundamentally rethinking how we manage this precious resource.
That's the ambition of cognitive radio. Its primary role is to
alleviate the spectrum scarcity by enabling what are termed unlicensed users, often called secondary users, as you says, to dynamically access spectrum that is officially assigned to
the intelligence of these cognitive radio systems hinges entirely on their ability to perform spectrum sensing. It's about intelligently identifying these spectrum gaps, those momentarily empty lanes on the digital highway where no one else is currently driving. It's their equivalent of having a super sensitive ear to the ground, or rather to the airwaves.
Exactly. It's akin to an automated, hyper-aware traffic monitor that can instantly, in real time, discern which
lanes are open and which are occupied without interfering with the existing traffic. This constant, vigilant listening is what allows for dynamic, efficient spectrum sharing.
Revelation we're going to unpack is an ingenious new weighted algorithm specifically designed to dramatically enhance their security and performance, ensuring our invisible highways remain both open and safe. Get ready, because this is where the airwaves get really interesting. With the stakes so high in this invisible battlefield of airwaves, the first line of defense is simply listening. But how do these radios actually hear what's happening on the airwaves to find available channels? Let's peel back the layers on that
foundational concept, spectrum sensing. What are some of the traditional methods that engineers initially devised to achieve this, and what were their inherent challenges?
Historically, there were
precise waveform, modulation scheme, and so on.
Which you might not always have.
Exactly. If you don't have that exact blueprint, it's effectively useless. Yeah, psychostationary feature detection is robust against noise, but it's computationally intensive, meaning it requires significant processing power and time, which isn't always feasible in dynamic real-time wireless environments.
So these methods were effective in theory, but often impractical or too demanding for the constantly shifting, unknown nature of real-world wireless spectrum. It sounds like they needed a simpler,
More adaptable approach, which brings us to a technique that became very popular, energy detection, or ED.
That's right. Energy detection became widely adopted precisely because it overcame the
It is. Instead of trying to identify the specific signature of a signal, ED simply measures the total energy present in a given frequency band. If the detected energy level surpasses a predefined threshold, the system assumes the channel is occupied. If it falls below, it deduces the channel is vacant.
so it's like a highly sensitive noise meter for the airwaves. If there's enough volume above a certain level, someone's transmitting. If it's quiet, the channel is open. That certainly sounds immensely practical, especially given you often don't know the
Exact specifications of every licensed primary user. This simplicity must be a huge advantage.
It truly is. The practical advantages of not needing prior information about the primary.
But in engineering, simplicity often comes with a trade-off. If energy detection is so easy and versatile, I have to imagine there's a but here. Why isn't it the definitive end-all, be-all solution for spectrum sensing?
You were astute to pick up on that. There's indeed a significant but. Despite its elegant simplicity, energy detection has critical weaknesses, particularly its susceptibility to inherent wireless channel weaknesses like shadowing and fading, which can severely
Compromise its efficiency and reduce its efficacy in real-world scenarios.
Right.
It's effective in a vacuum, but the real world is messy.
Shadowing and fading. Those sound like terms straight out of...
that a signal suddenly drops or disappears entirely. The physical structure literally blocks the radio waves, creating a shadow zone where the signal cannot penetrate or is severely attenuated.
So a cognitive radio might mistakenly think a channel is completely empty simply because a building or a hill is blocking its line of sight, even though a primary user is actively transmitting just on the other side. It's a literal blind spot.
Precisely. And then there's fading, which is more dynamic and often less intuitive. Picture yourself in a large auditorium.
And the sound system has multiple speakers, all playing the same music. As you move around the room, you might notice the music gets unexpectedly louder in some spots and quieter in others, even if...
So the signal strength isn't just blocked, it's fluctuating wildly, almost like it's winking in and out. Even if the primary user's transmission is constant and strong, it's the environment itself playing tricks with the signal.
That's an excellent way to conceptualize it. For cognitive radio relying solely on energy detection, this means a primary user's signal strength could momentarily dip below the detection threshold due to disruptive fading, even if the primary user is actively transmitting.
Okay, I see the problem.
This can lead the CR to mistakenly believe the channel is free, resulting in what we call a misdetection. And a misdetection means a secondary user could inadvertently transmit on an occupied channel.
if basic energy detection, for all its simplicity, is vulnerable to the fickle nature of the wireless environment, these blind spots from shadowing, and the unpredictable winking in and out from fading, what's the natural evolution? The direct answer to those limitations. How do we overcome these environmental challenges to achieve more reliable spectrum sensing?
The direct and powerful answer to those limitations is cooperative spectrum sensing, or CSS.
Okay, CSS.
Rather than putting all our eggs in one basket
and relying on a single cognitive radio unit to sense the spectrum, CSS intelligently leverages the collective intelligence of multiple users. It's essentially a spatial variety technique.
Exactly. Each of these individual cooperative secondary users, or CSUs, makes its own local observation of the spectrum. They then collaborate, sharing their individual sensing results with a central coordinating entity, the fusion center, or SC.
The fusion center.
The brain, basically. SC acts as the brain, yes. It takes all this distributed information, these multiple perspectives, and then makes a much more informed global decision about whether a specific channel is truly occupied or genuinely available.
That makes
Perfect intuitive sense. If one CSU is unfortunately shadowed by a large building, another CSU nearby might have a perfectly clear line of sight to the primary user.
Right.
By
The primary benefits are transformative. First, it significantly decreases the effect of channel variations on ED-based sensing. By aggregating data from diverse locations, you effectively smooth out or mitigate the localized fleeting effects of shadowing and fading. No single bad observation can derail the entire system.
It's huge.
Second, and critically, this directly improves detection performance. You get a much more robust and reliable overall sensing operation because you're building a
Consensus based on multiple independent measurements. It's a profound leap forward in accuracy and dependability for cognitive radio networks.
So cooperative spectrum sensing seems to solve
I can immediately imagine that when you have multiple users sharing information, you inadvertently create new points of potential attack. We've certainly heard about things like spoofing, where a malicious entity pretends to be a legitimate user, or jamming, where they simply flood a frequency with incoherent noise to block communication. But today, we're doing a deep dive into something even more insidious and strategically deceptive: Byzantine attacks.
You hit on a crucial point. While spoofing and jamming are indeed
Significant threats that network designers must address, the specific type of attack we're focusing on today falls under the umbrella of spectrum sensing data falsification, or SSDA.
What's truly fascinating and frankly quite alarming is that unlike a simple denial of service, where an attacker merely prevents communication or floods the network with junk, a Byzantine attack is about poisoning the information stream itself.
Okay, it's deception, not just disruption.
Precisely. It's far more subtle, deceptive, and difficult to detect. In this scenario, malicious users, MUs, don't just block a signal, they actively manipulate their initial values and transmissions to degrade detection
Performance intentionally. They report false information to the fusion center, meticulously designed to make the system believe something that is utterly untrue, leading to flawed global.
into its greatest vulnerability.
Exactly. And the devastating consequence is clear. The presence of these MUs can significantly disrupt the performance of the CRN. If the fusion center, become completely unreliable, or even cause severe and harmful interference to legitimate primary users. It's a fundamental breach of trust in the system's collective intelligence. That sounds like a true nightmare scenario for any dynamic
radio network. To fully grasp this threat, can we break down the specific model of how these malicious users falsify their data? The source mentioned equation 3, which details
intentional deception, not just a malfunctioning sensor or a noisy environment. This is a targeted attack.
Precisely. For malicious users, there are two distinct values at play. Their observed energy, which is what they actually detect in the spectrum, and then their falsified sensing results, EA, which is the deceitful value they report to the fusion center.
Okay, the real value versus the fake one.
Right. The extent of this difference, this manipulation, is quantified by a parameter called attack strength, which is a fixed value representing how much a malicious user deliberately alters their report.
There's also an attack threshold, which essentially serves as a benchmark that guides how the malicious user decides to falsify their data based on what they observe. It's a sophisticated
Indeed. The first type of deception is what we call a false alarm attack, or ASHN. In this scenario, the MU senses the PU's channel as vacant, not in use, but deliberately reports it to the FC as occupied, busy.
Okay, so they lie and say it's busy when it's actually free.
They're lying about the channel being busy when it's actually free, yeah.
So the channel is actually clear, ready for use, but the malicious user transmits false data saying it's completely occupied. What's the direct impact of
that particular lie on the cognitive radio network?
The immediate impact is that CSUs miss the opportunity to access the channel. To use your excellent traffic analogy, it's like a malicious traffic app.
Exactly. This causes all the honest drivers, the secondary users, to take unnecessary detours, leading to wasted time, increased congestion on other available lanes, and significant underutilization of precious spectrum. The CRN loses out on valuable opportunities to share spectrum, becoming inefficient and sluggish. It's a digital form of economic sabotage, preventing optimal resource allocation.
That's incredibly inefficient and frustrating for users. They're making a false alarm about a channel being busy, costing the
network valuable throughput. And what about the second, equally dangerous type of deception?
The second type is even more severe and potentially catastrophic. Misdetection probability, or AVILA 1.
Completely free. This is the inverse of the false alarm, but with far greater consequences, I imagine.
Exactly, and the consequence here is far more perilous. This misleading report can lead to interference between CSUs and PU, potentially disrupting communication between them.
Oh, wow.
Sticking with the traffic app analogy, this is like the app reporting a packed highway lane is completely empty, encouraging innocent drivers, the secondary users, to merge onto that lane, directly colliding with the primary users who are already there.
That's bad. Really bad.
This doesn't just cause a traffic jam. It can lead to severe data corruption,
critical system failures for licensed users, and a breakdown of essential services that rely on those primary transmissions.
Yeah.
For example, if this were a critical communication channel for emergency service,
you're not just dealing with wasted resources. You're actively causing harmful interference, potential system crashes, and undermining the very foundation of trust in a cooperative system. This highlights with absolute clarity why defending against these insidious Byzantine attacks is is not just a research interest, but an absolutely paramount objective for the future of cognitive radio, for the stability of our entire wireless world. Given the serious and multifaceted threats
Posed by these Byzantine attacks, it's entirely logical that many CSS algorithms under Byzantine attack have been introduced and studied in recent years. This isn't a new problem engineers
Another approach focused on computing the variance of the received sensing signal, where deviations beyond a certain variance were flagged as potentially malicious.
trying to spot statistical anomalies.
Exactly. We've also seen the development of trust value-based CSS algorithms designed to analyze and quantify the trustworthiness of each user's behavior over time. Algorithms based on reputation values were also explored, where users would accrue a reputation score based on their past sensing accuracy.
Reputation systems, interesting.
And finally,
There was the modified outlier removal spectrum sensing, or MORS approach, which used statistical methods like quartile conditions to identify and remove data points that seemed to be
prevented these past approaches from being the definitive answer we desperately needed.
that's a critical inquiry, and it gets right to the heart of why new solutions are constantly being sought. While these previous algorithms certainly made strides in mitigating certain aspects of Byzantine attacks, they often came with specific drawbacks that severely limited their effectiveness, their practicality, or both.
Okay, what kind of drawbacks?
For example, some approaches, like that trust value algorithm you mentioned, adopted a rather blunt strategy. They would simply remove MUs in the CRN once identified.
Just kick them out.
just kick them out.
Yeah.
The fundamental problem with this approach is that while it eliminates the malicious users, it can inadvertently degrade the overall detection performance of the network.
Equally serious one. You're throwing out valuable data and weakening the system, even if the intentions are good.
Exactly. It's an overcorrection that impacts the system's core functionality. Another significant limitation we've observed is with algorithms like the reputation value approach. While the concept of reputation sounds solid in theory,
It does sound good.
it requires the FTC to have knowledge of MU's use, meaning it needs a predefined list or a very robust, real-time method of identifying malicious users before it can assign reputation. In a dynamic, constantly changing wireless network where new devices
Can join and leave, and attackers can constantly change their identities or strategies, acquiring, maintaining, and verifying that prior knowledge in real time becomes incredibly difficult. Often
Precisely. Then we have the variance-based algorithm. Its performance suffers due to its elimination of MUs based on their variance exceeding the attack value. This method relies on the assumption that malicious activity will result in a statistically significant deviation in data variance. However, this method can be too rigid. Legitimate users might exhibit high variance due to perfectly legitimate environmental factors, such as extreme localized fading or shadowing.
Right, not necessarily malicious intent.
Not malicious intent at all.
such users could be unfairly excluded, again impacting overall detection accuracy. It's a bit of a blunt instrument, unable to discern intent from environmental noise.
And what about the more
Extreme values get cut.
Exactly. While effective for identifying extremely deviant values, It means it might not catch more subtle, sophisticated, or coordinated forms of malicious data manipulation. A clever attacker might not report wildly outside the normal range, but just subtly skew data points to influence the overall decision without being flagged as an extreme outlier.
The clever liar slipped through.
It's like only flagging the most obvious amateurish lies, letting the clever ones slip through.
Which the research showed leads to its comparatively poor performance against cunning and adaptive Byzantine attacks.
So previous methods either removed users entirely, which directly hurt
These accumulated challenges truly underscore the urgent need for something more robust. A sophisticated algorithm based on a weighted approach that defends against Byzantine attacks without falling prey to these costly trade-offs. It truly sets the stage for the breakthrough we're about to explore. So we've meticulously identified the insidious problem of Byzantine attacks and then analyzed the significant shortcomings of previous attempts to counter them. Now let's turn our attention to the heart of today's deep dive, the proposed efficient weighted algorithm.
What exactly is the core innovation here? What makes this approach fundamentally different from those that came before it?
The core innovation lies in its clever combination of dual
Exactly. It doesn't just try to quarantine the bad actors, it actively improves the system's ability to sense the spectrum accurately, mitigating the impact of the malicious users rather than simply eliminating them. And it achieves this through a soft combining technique, which means that each cooperative secondary user reports its computed energy values to the fusion center, rather than just a simplistic binary yes-no decision about channel occupancy.
It keeps the detail.
It retains far more granular
information. Yes.
Soft combining, that sounds like it's preserving more information, capturing nuance, which makes perfect sense if you're trying to intelligently weigh inputs rather than just accept or reject them.
The very first step, the algorithm's foundational move, is the calculation of the mean value dk for each CSU, as precisely described in equation 4 of the research. The Fusion Center doesn't just receive raw data, it first calculates the average reported energy value from each individual CSU within a specific ill-sensing instance.
Creating a profile for each user.
Think of it as building a consistent profile, a baseline, for each sensor in the network. It's understanding their typical voice or
Pattern of reporting on the airwaves, which is absolutely crucial for later spotting anomalies or deviations. This gives the system an initial fingerprint for each participant.
I understand. So it's
Review, I like that.
The algorithm meticulously checks how consistent each CSU's reported energy is with all the other CSUs in the network. It essentially calculates the difference between each CSU's reported energy value and the energy values reported by other CSUs. It's looking for consensus.
So it's not just comparing a user against an overall average, but comparing everyone's individual report against everyone else's report. A sophisticated, real-time peer review system at play.
Exactly, and this calculated difference, this measure of
Deviation is then rigorously compared against a threshold, which is the ingenious part. It's dynamically calculated.
not fixed, dynamic.
What's truly unique and adaptive here is that this
Furthermore, a unit step function, a fundamental concept in signal processing, is then employed to quantitatively count how many other CSUs are reporting values that fall within this acceptable range of consistency relative to a given CSU report. So it's not just a yes Yes, no. It's a precise count of agreement.
Okay, so it counts its friends in agreement.
Essentially, yes. If a CSU's report is wildly different from everyone else's, it will understandably get a very low consistency count, flagging it for closer inspection.
That dynamic thresholding makes immense sense. It means the system isn't easily fooled or thrown off by a sudden, legitimate environmental change that might affect everyone slightly differently, but
Based on that consistency check, the algorithm then proceeds to calculating the overall score for each CSU as precisely defined in equation 8. This score is essentially a normalized version of that consistency count, CK, transforming it into a standardized metric that is easily comparable across all users. A higher score directly translates to a higher degree of perceived consistency and, by extension, reliability within the collective.
Okay, so each CSU now has a refined, comparable consistency score.
this is where the rubber meets the road. How does the system then utilize these scores to actually pinpoint and identify the malicious users within the network?
This is where we arrive at the critical step.
Then it's a remarkably straightforward but effective comparison. If a CSU's score, SK, is greater than or equal to 1, the FSU will declare user as MU, otherwise it is HCSU. This is the first crucial and definitive step in pinpointing the potential attackers, those whose reports significantly deviate from the collective consensus.
So if your consistency score is an outlier, particularly above this average threshold in terms of how much you diverge, you're flagged as
Potentially malicious. But the brilliant part about this algorithm, as you mentioned, is that it doesn't just kick them out, right?
Right.
It goes a step further and assigns weights to their input.
Exactly. This is the nuanced part that sets it apart.
Exactly. For those less familiar, a z-score is a statistical measure that tells us how many standard deviations a particular data point, in this case a CSU's consistency score, deviates from the average score of all users. Think of the z-score as a weirdness meter or a deviation compass. Okay? A high positive z-score means they're very consistent with the average, while a low or negative z-score indicates they're an outlier, reporting values far from the mean, which is often
Characteristic of a malicious user. This gives a robust statistical indication of how much of an outlier they are.
And then these raw z-scores are refined into the final operational weights that will
indicates they are reliably above the average consistency, z-score 1. Their weight is slightly reduced by 1, z-score 1.
reduced, even if they're reliable.
Yes, and this is not to punish honest users, but to prevent a few exceptionally consistent users from disproportionately dominating the final decision and potentially skewing it, ensuring a more democratic collective decision. Conversely, if their z-score is lower, implying less consistency or potential maliciousness, their weight is slightly increased by 1, z-score plus 1.
Wait, if they're less consistent or malicious, their weight is increased. That sounds counterintuitive.
My previous analogy of trust calibration implied we'd want to reduce their influence. Can you clarify that subtle adjustment?
That's a crucial point for clarity, and it highlights the nuance of this
reporting values significantly above the mean consensus.
Like a false alarm attacker.
Right, characteristic of a false alarm type of malicious user who might be reporting busy when it's empty. Z-score plus 1 and Z-score 1 adjustments, while appearing simple, act as a final recentering and scaling mechanism after the outliers have already been identified in step 4. The overall effect of these adjustments, combined with how the z-score is derived, is that malicious
when it comes to the final global decision.
Okay, so the net effect is still reducing the bad actor's influence.
Precisely. Meanwhile, honest users, whose scores cluster around the mean,
CSUs maintain a strong, positive, and proportionate influence on the collective decision.
Okay, that clarifies it beautifully. It's a sophisticated adjustment that ultimately reduces the impact of the bad actors by calibrating their input rather than just simply boosting or cutting it. So think of it like a highly intelligent review project where everyone submits their vote. This algorithm doesn't just summarily pick out the unreliable ones. It calculates precisely how much to trust each person's contribution based on how consistent and reliable their past reports have been. It intelligently gives more weight to the
Trustworthy inputs and minimizes the influence of the deceptive ones. It's truly about trust calibration on the fly.
precisely.
Yeah.
And then for the final decisive stage, after all these intricate
Indeed. The Fusion Center leverages all these final weights to compute a weighted average of all the CSU's reported energy values. This resulting figure is a soft-valued decision statistic.
a soft value, not just a simple vote.
Right. Unlike previous methods that might have just taken majority vote, this is a much more nuanced, probabilistic assessment. This soft-value decision statistic is then compared against a global decision threshold to make the ultimate network-wide decision about whether the
channel is actively occupied, hypothesis H1, or currently available, hypothesis H0.
Okay.
If we connect this to the bigger picture, this complex multi-stage weighting system
exactly doesn't throw out the data. It just applies a highly discerning, dynamically adjusted filter based on its calculated trustworthiness. This fundamental difference from simply removing users is what gives it its breakthrough performance.
That is incredibly powerful. It's like the system has developed a highly sophisticated intuition, learning who to trust more and who to trust less, and then it adjusts its collective listening accordingly. It avoids completely shutting down an input unless it's truly irredeemable.
Which preserves more data for the overall decision. This seems like a profoundly sophisticated way to manage deception and maintain integrity in a complex cooperative environment.
So, what do the rigorous results of the simulations tell us about how well this algorithm actually performs when put to the test in conditions designed to challenge it?
The researchers indeed ran extensive simulations, a critical step to validate their theoretical framework. They used a controlled environment with specific parameters. A total of 10 users in the network, 5 of whom were maliciously falsifying data.
Half the network was malicious.
Yes, a significant challenge, operating at a challenging signal-to-noise ratio of 90 to 10 dB.
and repeating the process over 10,000 iterations to ensure statistical significance. This meticulous setup allowed them to rigorously test the proposed algorithm against
Needed detection probability. How well it spots an occupied channel.
Exactly. Detection probability for our listeners is simply the measure of how accurately the system correctly identifies when a primary user is actually occupying a channel. This isn't just a technical win, it's a fundamental shift in how resilient these networks can be. You can imagine a world where your wireless connection is virtually unhackable talking about here.
That sounds like a game changer. How did this new algorithm stack up against those existing methods we previously identified as having significant limitations? Give us some concrete numbers.
The comparison.
That's a staggering 43.79% improvement over that particular method.
Huge difference.
And against the Moore's algorithm from source 16, it still showed a robust PD of 0.602, which represents a very significant 22.91% improvement.
Wow. That's not just a marginal gain in efficiency, that's a truly substantial leap in its ability to correctly identify occupied channels. What specific characteristics of this proposed algorithm allow it to excel so dramatically compared to the others?
The paper clearly articulates the reasons, and they align perfectly with our earlier discussion of the previous
method's limitations. The 10 algorithm, you'll recall, suffered from completely eliminating malicious users based on their variance.
The blunt approach?
The blunt approach, yes. As we discussed, it often
The proposed weighted approach, however, intelligently de-emphasizes bad data rather than summarily removing it. This allows it to judiciously leverage all available information more effectively while intelligently mitigating the malicious influence, resulting in its superior performance. It's the nuance of the weighting versus the bluntness of elimination that truly makes the difference.
So it's about being smarter, not just harsher. That makes perfect sense. But in the unpredictable world of cyber threats, attackers aren't static.
What about its robustness against increasing attack probabilities? Because you mentioned that malicious users can vary their attack strength and the probability of their deceptions. How does the algorithm...
However, a key finding that speaks volumes about this algorithm's resilience was that the detection performance remains robust even in the presence of high attack probabilities. For example, even when both IA and IA1 increased significantly from 0.5 to 0.7, the proposed algorithm's PD only degraded by a mere 6.31%.
Only 6% drop. That's impressive.
It demonstrates impressive resilience, meaning it holds up exceptionally well even when attackers are highly
active and aggressive in their deception attempts. It doesn't fall apart under pressure.
That's immense for practical deployment, especially in dynamic environments where you can't always predict the precise level or intensity of...
malicious user manipulates their data.
By having the liars.
Exactly. The algorithm approaches nearly 100% accuracy in identifying the malicious users when this delta value reaches or exceeds 0.4. This is a very strong indicator of its precise ability to identify attackers based directly on the magnitude of their data falsification. It's not just resisting, it's actively identifying the source of the problem.
And does it work even when the attackers are trying to be subtle, perhaps only slightly skewing data, or when there aren't many of them in the network? Because sometimes
The most dangerous threats are the ones that fly under the radar.
Yes, that's what Figure 5 in the research beautifully illustrates. The overall score S for the MU is higher when compared to the scores of other HE.
Flagging them as MUs, even when their deceptive activity is minimal and they're trying to blend in.
so it catches the sneaky ones too.
This means it's not just good at handling large-scale overt attacks, but it can sniff out the more covert, subtle ones too.
That's incredibly impressive. It gives network operators a powerful tool for proactive threat identification. But what happens when the number of malicious users in the network increases? Is the system overwhelmed if there are more bad actors to deal with? This is often where many algorithms completely unravel.
And this is truly where the proposed algorithm delivers a critical breakthrough,
distinguishing itself dramatically from its predecessors. Existing algorithms, such as those from 10 and Morris 16, consistently demonstrate a reduction in the probability of detection.
Is a game changer for real-world CRN deployment, where the number of malicious actors can vary wildly and unpredictably.
Give us some numbers on that, because that sounds like a fundamental shift in resilience. The more malicious actors, the more systems usually falter, so a sustained performance here is truly remarkable.
Consider this dramatic comparison. With 3 malicious users present in a network of 10 total users, the Morris algorithm's detection probability degraded by 13.03% compared to a scenario with no malicious users.
Okay, noticeable drop.
The 10 algorithms saw an even more substantial degradation of 33.23%.
A third worse. Ouch.
But the proposed algorithm, it experienced only a minor degradation of 0.78% as the number of malicious users increased.
Genuinely remarkable. It means that the system can confidently handle significant malicious user populations without a major hit to its core function of detecting spectrum use. And finally, what about its performance in the most challenging communication environments, like when signals are weak or the airwaves are inherently noisy? Does it still hold up when conditions are far from ideal?
Here too, the proposed algorithm shines, extending its practical applicability significantly. Figure 7 from the research illustrates its effectiveness across different
signal-to-noise ratio, SNR levels. The core finding is that the proposed algorithm significantly enhances detection performance, even when subjected to very low SNR levels.
Dismal 0.088 under the exact same difficult conditions.
Wow, huge difference again. So even when the legitimate signals are barely audible above the static, this algorithm can still discern who's there and who isn't, and whether a channel is truly occupied, with significantly greater effectiveness. That expands its practical applicability immensely, right? It means it can work reliably in real-world scenarios where perfect signal conditions are a luxury, not the norm.
Exactly. This superior performance in low SNR scenarios is absolutely vital because
wireless channels are inherently noisy and prone to various forms of interference. An algorithm that can cut through that noise and still detect primary users accurately while simultaneously
What an illuminating deep dive into the unseen complexities of our wireless world. We began by acknowledging the fundamental challenge of crowded airwaves, and then explored the brilliant adaptive solution offered by cognitive radio for dynamic spectrum access.
And we meticulously honed in on the critical foundational task of spectrum sensing, particularly highlighting the inherent vulnerabilities of basic energy detection. We then saw how cooperative spectrum sensing, while a
powerful improvement, inadvertently opened the door to new and insidious security risks, especially from those deceptive Byzantine attacks.
Right.
Where malicious users actively
nuanced and clever forms of digital deception.
But the real revelation, the true breakthrough, was the innovative new weighted algorithm we've unpacked today. We walked through its remarkably sophisticated multi-step logic, from calculating individual user consistency scores and dynamically adjusting thresholds to precisely pinpointing malicious users and then assigning carefully calculated weights.
Those all-important weights.
These weights effectively mitigate their deceptive influence without discarding all their data, allowing the system to learn and adapt.
And the proof, as they say, was definitively in the performance. This algorithm consistently showed a remarkable improvement in detection probability, dramatically outperforming existing
communication environments.
This pioneering work genuinely contributes to significantly strengthening the security and reliability of cooperative spectrum sensing and cognitive radio networks. It's a vital addition to the field, profoundly enhancing how we can manage and secure our increasingly complex and interconnected wireless world.
And that leaves us with a truly provocative thought for you, our discerning listener. As our world becomes increasingly interconnected and reliant on dynamic, self-organizing networks, from the smart
grids that power our cities, to the autonomous vehicles that will navigate our streets, and even the decentralized finance systems built on trustless architectures.
Big implications.
How might the